All right, well, there are many different coordinations geometries that can exist, especially when you have transition metals involved. And so here's kind of a survey of some of the more common ones. There's a lot, especially when you get to higher coordination numbers. But some of these are VSEPR type geometries, so like trigonal planar. Remember, the VSEPR type geometries are the geometries that maximize the distance between the ligands or the pentatoms, whatever you want to call them. And so trigonal planar, right, tetrahedral for 4 coordinate, trigonal bipyramidal for 5 coordinate, octahedral is your VSEPR geometry for 6 coordinate, pentagonal bipyramidal, that's your coordination number for your 7 coordinate VSEPR geometry. Square, antiprismatic, tri-capped, trigonal prismatic are your VSEPR geometries for 8 and 9. But then there's all these other different geometries that can exist, and oftentimes, depending upon the metal complex, are the most stable geometries. And this shows you that VSEPR is basically totally not applicable to transition metals and to F-block chemistry. Okay, so for example, many coordination complexes that are 4 coordinate are square planar. Many transition complexes have some sort of distorted octahedral shape. These are not VSEPR geometries. You can have square pyramidal T-shaped complexes for 5 and 3 coordinate systems, and a wide variety of higher coordination number geometries that all are usually pretty similar in energy. Okay, but what we're going to start out with is just looking at some of the complexity that can arise in terms of isomers. And so, obviously, if you have a square planar system with 4 different, 4 of the same ligands, okay, there's only one way you can connect those and still have square planar geometry. So that'd be like Ma4. Okay, remember isomers are structures that have the same empirical formula, but are connected in different ways. And so consider if you have an Ma3b square planar complex. So that would be a complex like this, right? Basically means one type of ligand that only appears once, and then the other 3 ligands are all the same. And so you could draw this 4 different ways, but these are not isomers. These are all equivalent, which is why I put the equal sign here, right? One thing that's useful here is to look at cis and trans relationships. Cis means next to, okay? So like this A is cis to this B, this A is cis to this B, but this A is trans, it means across from this B. So this A is trans to the B. And you can see that the B is always trans to 1A and cis to 2A's. So that's true here, right? It's trans to this A and it's cis to 2A's. Here it's trans to this A and cis to 2A's. Here it's cis to 2A's here and trans to this A here. So all these, that's when you track these cis and trans relationships, that's another way of just seeing if the structures are equivalent. Another easy way to look at this is, all I'd have to do is take this structure right here, and all I'd have to do is rotate it 90 degrees, right? If I rotate this 90 degrees clockwise, I'm going to get this structure, rotate it another 90 degrees, I'm going to get this structure, and another 90 degrees to get that structure, okay? But now let's go to something a little bit more complicated where we have 2 ligands of one type, of A type, and 2 ligands of B type. Now, you can draw them, the 2B's cis, okay, and the 2A's cis. You can draw them in 4 different ways. I'm rotating it 90 degrees. Or you can draw the 2B's trans to one another and the 2A's trans to one another. And there's 2 different ways to draw that, both equivalent. So this tells you that you have 2 different geometric isomers, and these have different properties. They have different physical properties, different melting point, different colors, oftentimes, and different reactivities. All right, so these are isomers, and they would have to be made in different ways, would have to be synthesized in different ways. All right, so we call these the cis and trans isomers. Let's think about if you had Ma2BC. Okay, so you have 2 ligands that are different in B and C, and then the 2 A's are the same. This, it turns out, there's only 2 isomers, cis and trans. And it's called cis and trans whether or not the 2 A's are cis or trans to one another. So are the A's cis to one another? that's going to look something like this. If this A's are trans to one another, it's going to look like this. Again, these are going to have different properties. What if you have 4 different ligands? We can call that MABCD. Well, then it turns out you have 3 different possibilities, okay? And basically, the way you can think about this is for every one ligand, you have the option of being trans with 3 different partners. So this is the AC trans pair, the AB trans pair, and the AD trans pair, right? So A was trans to B in one, trans to C in the other, and trans to D in the other. So there's 3 different isomers here. Again, all these will have different physical properties, different reactivities. So you get this really rich chemistry that can be invoked by just very simple coordination modes, okay? Now, here's something interesting I want to make a connection to. You may remember from your organic courses, introductory organic courses, that if you have a tetrahedral complex, right, carbon is tetrahedral, that you are going to have, and you have 4 unique ligands, right? So like a carbon with 4 unique ligands, 4 unique atoms, 4 unique functional groups on the end of the carbon, that is chiral, okay? And so a question to think about is, are square planar complexes with 4 unique ligands chiral as well? The tetrahedral centers, they are. Are they with square planar? The answer is no. And the really easy way to show this is that there's just a mirror plane here, okay? These are flat. Remember, square planar, it's plane, right? These are flat. So any square planar molecule has a mirror plane in the plane of the molecule. Takes the top half of each atom and moves it to the bottom half of each atom in the mirror plane, okay? And so these molecules actually have CS symmetry. They have identity and they have a mirror plane. But because they have a mirror plane, we know that any molecule that has a mirror plane cannot be chiral. That's definitely true. We know that. So these are not chiral. There's no enantiomers of these. The mirror image is superimposable. Remember, something that we stressed early on in the molecular symmetry chapter was that, yes, any molecule that has a mirror plane is not chiral. But if you don't have a mirror plane, it doesn't necessarily mean you're a chiral. There are weird point groups like S4, for example, where you don't have a mirror plane, but you have an improper rotation axis, and you're still not chiral, okay? So mirror plane, not chiral. No mirror plane, you don't know, okay? That's a thing that sometimes is taught wrong in organic chemistry. All right, so in the next videos, we're gonna go over some isomers of higher coordination modes of geometry, and it gets really interesting the higher you go, as you might be able to imagine.